Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025, just yesterday. This paper introduces a new framework that boosts the accuracy of translating math problems into formal code from 54% to 84%. The paper is titled CriticLean, Critic-Guided Reinforcement Learning for Mathematical Formalization. And this new approach significantly improves the reliability of these automated systems. This paper tackles the challenge of turning natural language math into formal, computer-understandable code, a process called formalization. Also, the authors shared their work on GitHub. And it's not just the implementation. You'll find the actual CriticLean models, their new CriticLeanBench for evaluation, and the massive FineLean corpus dataset they created. It's a really comprehensive resource with all the key components from the paper for researchers to use. On Hugging Face, you'll find their 8 billion parameter model, along with the datasets and usage examples for fine-tuning and reinforcement learning, ready for you to try out. Alright, so this diagram really lays out the whole CriticLean framework. It starts with a math problem in plain English. An auto-formalizer then tries to translate this into Lean, which is a formal proof language. The generated code goes through a two-step check. First, a standard Lean compiler looks for basic syntax errors. If it finds any, the system tries again. But the crucial step is the second one. A special critic model, CriticLeanGPT, checks if the code's logic actually matches the original problem's meaning. This critique loop is the key innovation. So, to properly test that new critic model, the authors needed a very high-quality benchmark. And this figure shows exactly how they built it. It's called the CriticLeanBench, which is essentially a standardized test to see how well the critic can spot errors. The process involved two main stages. First, an automatic filtering step used a model called DeepSeek R1 for an initial check. Then, crucially, human experts performed a detailed manual review, ensuring the final questions were accurate and logically sound, creating a really robust evaluation tool. This table then details the exact composition of that CriticLeanBench. It contains a total of 500 problems, split right down the middle, 250 correct pairs and 250 incorrect pairs. What's interesting is how they were verified. For the incorrect pairs, 200 required a human to spot the logical error, while only 50 had simple syntax errors a compiler could catch. This detail really underscores the need for a semantic critic. And these aren't simple problems either. The average length is over 700 tokens, showing the benchmark is designed to be challenging. Moving to the results. This table shows how different models performed on that CriticLeanBench we just discussed. It compares a range of standard LLMs against the author's own CriticLeanGPT models. While models like Gemini 2.5 Pro score high in overall accuracy, the author's models really shine at their specific task. For example, their QN332BRL model achieves an impressive 87% accuracy. More importantly, it has a very high true negative rate, which is a key metric here. It measures how well the model correctly identifies incorrect code, which is exactly what you want a good critic to do. So beyond the benchmark scores, this final table really shows the practical impact of the whole system. Here, the authors used human evaluation to check the accuracy of the auto-formalization process. The baseline model, Camino Auto-Formalizer 7B, only got it right 38% of the time. Adding a standard compiler check helped, bumping accuracy up to 54%. But look at this. When they added the CriticLean feedback loop, the accuracy jumped all the way to 84%. This really drives home the main point. Compilers catch syntax, but the critic catches meaning. So that 84% accuracy figure really says it all. The big takeaway from this work on CriticLean is that focusing on the critic phase, that is, checking if the formalized code actually means the same thing as the original math problem, is essential. Simply checking for code errors isn't enough. By using a critic-guided approach with reinforcement learning, where the model learns from its mistakes, the authors built a much more reliable system. They've also released some fantastic open source tools to help push this field forward. That's all for this week's AI Research Roundup. Thanks for tuning in.